All right, so today we're doing this page right here, and we're looking at air masses. All right, now, if the only thing that determined our temperatures is how much energy we got from the sun, then like on April 2nd, we get more energy from the sun than we do on April 1st. So April 2nd should be warmer than April 1st. In April 3rd, we get more energy from the sun than we do on April 2nd. So April 3rd should be warmer than April 2nd. April 4th, we get more energy from the sun than April 3rd. So April 4th should be warmer than April 3rd. And if we looked at like a farmer's almanac or something like that and look at the averages for 100 years, you probably would find that April 2nd is warmer than April 1st, April 3rd warmer than April 2nd, and so forth. However, in any one given year, April 1st, it may be 50 degrees. April 2nd, it might be 30 degrees. April 3rd, it might be 60 degrees. April 4th, it might be 20 degrees. The temperature could fluctuate quite a bit from day to day. So obviously then, the sun, how much energy we get from the sun isn't the only thing that's affecting our temperature. So what is affecting our temperature? A lot of times, air masses affect our temperatures from day to day. So what happens is, if I have a big mass of air that formed down south, where the sun's higher in the sky, that mass of air would have more energy in it. And then if that mass of air moved to where we are, it's bringing all that energy and warmth with it, giving us warmer temperatures. Or if there's a chunk of air from northern Canada, where the sun is lower in the sky and it's getting less energy, if that were to move down where we are, it's going to bring that colder temperatures with it. So that's what we're looking at today is air masses. All right. Now, let's say I have a warm, moist air mass. All right. Warm, moist air has very low density to it. And what happens is air that has a lower density, it tends to rise. All right. So look. Now, if you remember what air pressure is the weight of the air on top of you. Now, if the air above me is rising, I'm not going to feel as much weight pressing down on me. So rising air is low pressure. Right? So I have this warm, moist air rises, and something has to take the place of it. So air from the sides comes in to take the place of it like that. All right? So the air is converging and then rising. All right. Now that's a side view of what's going on. Let's say I was going to do a top view. If the air right here is rising, stuff from the side would be coming in to take its place. Like that. So the air is coming together and rising because it's warm and moist and less dense. All right, now, so the arrows are coming together, so it's said to be converging around low pressure. Now, if the Earth did not rotate, then that wind might go in nice straight lines like that. But because the Earth is rotating and you have something called the Coriolis effect that causes the winds to bend, the wind does not go in nice straight lines in the low pressure. Rather, it goes into the low pressure center curving. And in the northern hemisphere, where we live, it curves like that. So not only do the arrows come in, but they spiral. And around low pressure in the northern hemisphere, it spirals counterclockwise like that. Right? So it spirals counterclockwise, goes in, and then rises. All right? Now, whenever air rises, the higher up it goes, it cools down. And eventually it cools down to a point where you start to get condensation and clouds forming. So with low pressure, you get lots of rain and clouds. So low pressure is lousy weather. Right? Rainy, cloudy weather is low pressure. And because low pressure is associated with storms, it's said the air is said to be unstable. All right? So pilots don't like flying in unstable air because it's stormy conditions. Another word sometimes used for low pressure systems is a cyclone. So cyclone is another word for low pressure side. All right, so that's a low pressure air mass. All right, high pressure. Right here, I have air that's cool and dry. All right. Now, air that's cool and dry is more dense. So what does more dense air want to do? More dense air is going to sink. It sinks, hits the ground, and then it's going to spread out like that. All right. So the air is sinking and then diverging outward. Now, a top view of this, how it might look, the air is sinking and then spreading out. And again, if the Earth did not rotate, it might go out in nice straight lines like that. Right? However, the Earth is rotating and we have the Coriolis effect. So instead of going out in straight lines like that, around high pressure, the air rotates this way. So in the northern hemisphere, high pressure, not only does the air go out, but it also rotates clockwise. So it's divergent and it spins clockwise around high pressure. Now, with high pressure, because the air is sinking, it's heating up. As air heats up, it becomes drier. So with high pressure, you have clear skies. So sunny weather, clear skies is what you get with high pressure. Because the air is sunny and clear, the air is said to be stable. And another word for high pressure system is an anticyclone. All right. So if the air pressure is getting worse, if the air pressure is decreasing, that means you got a low pressure center and you're more likely going to have rain in the near future. If your air pressure is rising, that means you likely have high pressure approaching your way and you have nice weather coming. So how they used to make weather forecasts in the old days is they used to take this device called a barometer, which measures air pressure, and you'd mark what the air pressure is like right now, and then maybe you check the air pressure a couple hours from now, and if during those couple hours the air pressure had been going up, then I know high pressure is approaching and the forecast is going to be good. If I checked what the air pressure was in a couple hours later and it was lower, that means I got low pressure coming and I'm probably going to get a storm of some sort. All right. Now, the thing that determines, whether it's going to be a cool, dry air mass or a warm, moist one, is based on where that air mass comes from, and we call that the source region. So a source region is a geographic region where air masses form and acquire their characteristics. Right? So there's basically two things you're looking for in air mass. One thing is going to determine whether it's going to be a relatively warm air mass or a cool air mass. The other thing is going to be whether it's going to be a wet air mass or dry air mass. So the thing that determines whether it's going to be warm or cold is whether it comes from the north or the south. If the air mass comes from the south, it's said to be a tropical air mass, represented by the letter T. If it's coming from the north, it's called a polar air mass, represented by the letter P. Or if it's coming from the far north, we can call it an Arctic air mass, letter A. So warm, cold, very cold. And the other thing is whether it's going to be a dry air mass or a wet air mass. So if an air mass originates over land, it's called a continental air mass. So that's dry. And if it forms over water, it's called a maritime air mass, represented by the letter M, and that's a wet air mass. So you put these together and you end up with several variety of air masses. You have MT's maritime tropical, that is over water from the south, so it's warm and wet. MP's maritime polar air mass, over water from the north, so it's going to be cold and wet. CT's continental tropical over land from the south, so it's warm and dry. CP is continental polar, so it's over land from the north, so it's cold and dry. CA, continental Arctic, over land from the far north, and that's going to be very cold and dry. So where we find these air masses in North America, if it's in the Gulf of Mexico, that's over water from the south, that would be an MT air mass. If it formed over Mexico proper right there, over land from the south, that would be a CT air mass, continental tropical. If it formed over here, west of Mexico, that's over water from the south. That'd be a maritime tropical air mass as well. If it formed like right here, which would be like central Canada, over land from the north, that'd be a CP air mass. If it formed over here, that's over water from the north, that'd be an MP, maritime polar air mass. Same thing holds true over here, over water from the north, so that'd be an MP, maritime polar air mass. Then if it comes from way up here, it'd be continental Arctic. Now, for us in New York State, and again, my drawing of North America is horrible, I know that, but New York State would be roughly about there. There's two air masses that we get more than any other. The two that we most frequently get is the maritime tropical air masses that'll work their way up here and give us warm, wet conditions, or we get these continental polar air masses come down from Canada and give us colder, drier conditions. Those are the two that by far we get the most of. We don't get very many continental tropical air masses affecting us over here. One reason, because North America really isn't set up very well for continental tropical air masses, because there's really not very many big land masses down here for them to form. Another thing is at this latitude, the prevailing winds kind of blow that way as well. Another thing with the maritime polar air masses, we don't get too many of those. I mean, we're relatively close to that, but at this latitude, the winds are typically blowing that way, so the air masses that form there are typically going to go that way, not come back this way. They can come back this way once in a while, but not too often. And then these guys here are really far away, so you don't really get that coming all the way over here too often. We get lots of the continental polars. Every once in a while, we get one of these continental Arctic ones. That's where we might have the temperatures like in February, where it's like, 0 degrees for a week straight. That's when one of these guys come down, continental Arctic. Now, one little interesting thing here about the continental Arctic, if you look at continental Arctic, where it's forming here, it's up this section right there, which is actually the Arctic Ocean. So you might be like, wait a minute, if that forms over the ocean, why isn't that a maritime Arctic air mass? Well, even though that's the ocean up there, the ocean up there is usually frozen over. So if the water's frozen over, there's no moisture evaporating off of it. So even though technically it's water, it acts like land because no water's evaporating off of it. So that's why it's usually considered continental. And if you notice, there's not even a maritime Arctic air mass listed right there, because the Arctic Ocean is usually frozen over. Now, in your reference tables, a couple things I want to show you. On page 13, all right, first off, it has the air masses listed right there. So you don't have to memorize the names of the air masses, because it's listed right here, MP maritime polar, MP maritime tropical, and so forth. It's all listed right there. So if you see like a CT on a weather map, you don't have to memorize what it is. You can just come here and say, yeah, CT is continental tropical. So it tells you the names. However, it doesn't tell you in your reference tables what the weather's like there. It just tells you the name of it. Now, you should be able to figure out what the weather's like if you know that tropical means hot and polar means cold, and continental means land, so it's dry, and maritime means water, so it's moist. But anyway, so that shows you the names of the air masses right there. Another chart to point out is this guy over here, which I'll bring down. So this chart over here is the pressure conversion chart. So it has 3 units on here. It has millibars, which is the metric unit for pressure. It has inches of mercury, that's more the English unit for pressure. And then it has atmospheres, that's another unit for pressure. Now, atmospheres isn't one that's used for weather very often. Millibars and inches are the ones that are frequently used for weather. Atmospheres, you might use that like if you're comparing the air pressure on the surface of Earth to the surface of Venus or something like that. You may say our air pressure is so many atmospheres, well on Venus it's so many atmospheres, something like that. So it's just a different scale. I mean, it's like, if you're measuring distances, this might be inches, this might be centimeters, and that would be miles. I mean, technically it's measuring the same thing, but you wouldn't use that really to measure weather stuff, because weather stuff's more precise. But anyways, that is another method, another unit for measuring pressure. But anyways, the millibars side is pretty straightforward. It's just going up 996, 997, 998, 999,000, so forth. So it's going up by ones. The inches of mercury side is a little bit trickier to read, only because like there's 30 right there. One line above 30 is not 31. 31 is way up there. One line above 30 is not 30.1 either, because 30.1 right there. Each of these little lines is actually going up by 100th. So that's 30, that's 30.01, 30.02, 30.03, 30.04, 30.05, 30.06, 30.07, 30.08, 30.09, 30.10. So each one of those goes up by 100th on that side. But pretty easy chart to convert. On tests, these pressure conversion problems should be like a gimme points on a test. But anyways, so that is air masses and how to use the pressure chart right here.